So, in the last video, we have started crystallography and we have explained different planes in a crystal lattice. In continuation of that, today we shall discuss different planes in cubic crystals and different types of cubic crystals, simple cubic, body centered cubic and face centered cubic crystals, and what are the interplanar distance in this type of crystal lattice, and what is the ratio, and how to identify the structure of the crystal in case of cubic lattice, and also we have to derive Bragg's equation to find out the glancing angle, and also we have to explain today Bragg's spectrometer in the identification of the crystal structure. So, we shall start now from this lattice planes in a cubic crystal. So, in case of cubic crystals, there are three types. One is simple cubic lattice. Another one is body centered cubic lattice, BCC. Another one is face centered cubic lattice. In case of simple cubic lattice, there are only atoms in the corners of a cube, and the planes in the x direction, y direction and z direction, different planes are there. So, these parallel planes, how to represent these parallel planes, so that we have to discuss today. So, if you see this plane, this is the plane, this is at the distance a in the x direction and infinity in the y direction and infinity in the z direction, and the Miller indices HKL for this plane is 1, 0, 0. Miller indices 1, 0, 0. Weiss indices for this plane is 1, infinity, infinity. So, 1, 0, 0 plane is represented like this. In case of simple cubic lattice, this is 1, 0, 0 plane. Other planes are now you see this. Now I will show you one more plane. You see this plane. So this is the plane. This plane of simple cubic lattice, which bisects the intercept in the x direction is 1 unit, and intercept in the y direction is also 1 unit, and it is perpendicular to it is parallel to z axis. Therefore, HKL in this case is 1, 1, 0. Miller indices for this plane is 1, 1, 0. Weiss indices 1, 1, infinity. This is another plane in another direction. One more plane we can write here. So, 3 planes in 3 different directions. So, this is another plane. This plane is represented like this: unit intercept in the x direction and unit intercept in the y direction. This bisects all the axes at unit intercept in all the directions. Therefore, Miller indices for this is 1, 1, 1. So, this is 1, 1 plane, and Weiss indices is also 1, 1, 1. So, there are 3 planes in different directions for a simple cubic lattice: 1, 0, 0 plane, 1, 1, 0 plane and 1, 1, 1 plane. Now, if you take, you can find out the distance between these parallel planes. You can derive an expression to find out the distance between these parallel planes, 1, 0, 0 planes. A number of parallel planes are possible in a cubic lattice which are parallel to each other. the interplanar distance which are parallel to each other, interplanar distance 100 planes, a number of 100 planes are there, distance 110 planes and 111 planes. We can derive an expression to find out the distance for this parallel planes. d HKL is equal to a by square root of h square plus h square plus k square plus L square, h square plus k square plus L square. We can find out the interplanar distance for different planes. For example, the distance between two parallel planes in this direction, the distance between these two parallel planes can be calculated using this equation, which can be easily derived. DHKL is equal to a by h squared plus L squared. The distance between these two planes is, that is D100 plane is equal to a by square root of h square is 1 square plus 0 square plus 0 square, that is equal to a unit intercept. So, distance between these two planes, parallel planes, for this 100 plane is D100 is equal to a by 1 square plus 0 square, that is equal to a. Now, the distance between parallel planes of this plane, distance between parallel planes of 110, that can be calculated, that is D110 is equal to a by square root of h square plus k square plus L square, that is equal to a by square root of 1 square plus 1 plus 1 is 2, square root of 2. So, this is the interplanar distance between this 100 planes. Similarly, we can calculate the distance between D111 plane. D111 plane, a over square root of 1 square plus 1 square plus 1 square, that is equal to a by root 3. Therefore, three types of planes are possible in three different directions. D100 plane, interplanar distance is unit intercept, that is a 110 plane a by square root 2, 111 plane a by root 3. So, this is the interplanar distance. Now, other possible crystal lattice for this cubic lattice is body centered cubic lattice, body centered cubic lattice. So, apart from atoms or molecules in the corner, we have one extra atom, one extra center at the center of this cube. That is why this is called body centered cubic lattice, BCC, body centered cubic lattice. In case of body centered cubic lattice, apart from these 8 corners, there is one atom at the center of the cube. Here also 3 planes at different direction parallel to each other are possible. One plane is this plane which bisects the unit intercept by half. Therefore, HKL in this case, Miller indices, this is half, Miller indices 200 and V's indices for this, V's indices half, infinity, that is one plane. Another possible plane is this one. This is another possible plane which involves the body centered particle here, and this plane is as this equal to this, that is 1 1 0 plane, 1 1 0 plane. Another possible body centered cubic lattice is which bisects all the directions by 2. So, this is the possible plane here. This is represented by 2 2 2 plane. So, 3 possible planes are possible in 3 different directions. One is 2 0 0 plane, another one is 1 1 0 plane, another one is 2 2 plane, and here this index is half infinity infinity. In this case, this indices is 1 1 infinity, and here it is half and half. Reciprocal of this Miller indices is these indices. Similarly, we can calculate the interplanar distance here for all the 3. So, interplanar distance DHKL for this plane, for 2 0 0 plane, DHKL, that is 2 D 2 0 0. This can be calculated, which is equal to A by square root of h square plus k square plus l square, A over square root of h square 2 square plus 0 square plus 0 square, which is equal to square root of 2 square is 2. So, that is A by 2. A by 2. It is the interplanar distance between these 2 0 0 planes in this body centered cubic lattice, and it is A by 2. Similarly, the distance between the parallel planes of this 1 1 0 is equal to A over square root of 1 square plus 0 square plus 0 square, that is equal to A by root 2, as in this case A by root 2. And another plane D 2 2 2 plane is A over square root of 2 square plus 2 square plus 2 square, that is equal to A over 2 square is 4, 4 plus 4 plus 4, 12 can be written as 12 can be written 12, 2 square is 4, square root of 12, square root of 12, it can be written as 6 into 2, 6 into 2 is 12, 6 into 2. So, 6 into 2, square root of, not like that, 2 square plus 2 square, 4 plus 4, 8 plus 4, 12, square root of 12 can be written as square root of 6 into 2, square root of 6 into 2, square root of 2 and square root of 6. Square root of 6 is root 2, square root of root 2 is 1, root 6. So, A is equal to A over A by 2 square plus 2 square plus 2 square, A by 2 root 3, A by 2 root 3. This can be written like this. Similarly, we can calculate the interplanar distance for another type of crystal, that is body centered, that is face centered cubic lattice. I will write this face centered cubic lattice. So, apart from these centers, there are atoms or molecule at the faces, face centered cubic lattice. This is one face, this is another face, another face, another face. This face is one here and this face is one here. So, in the bodies, in the face centered cubic lattice, apart from the corners, there are centers at the faces. That is why these are called face centered cubic lattice. In the face centered cubic lattice, there are atoms at all the three faces. At all the three faces, atoms are there. These are called face centered cubic lattice. So, here what are the planes possible in case of face centered cubic lattice? Of course, one center is this, one plane is this. This is 2, 0, 0 plane, 2, 0, 0 plane. Another one is 2, 2, 0 plane. 2, 2, 0 plane means which bisects the x-axis at half and y-axis at half. Another one is parallel to z-axis. Y-axis half, another one is parallel to z-axis, and this is 2, 2, 0 plane. 2, 2, 0 plane, and another possible plane is this one. This is 1, 1, 1 plane. 1, 1, 1 plane. So, 2, 0, 0 plane, 2, 2, 0 plane, and 1, 1, 1 plane in case of face centered cubic lattice. One is 2, 0, 0. Which indices is half infinity, infinity. Here 2, 2, 0 plane. In this 2, 2, 0 plane, which indices half, comma half, and infinity. And here it is the unit intercept 1, 1, 1. So, we can calculate the interplanar distance using this equation. DHKL is equal to A over square root of h square plus k square plus l square. Now, let us find out the interplanar distance for this plane 2, 0, 0, D 2, 0, 0. The interplanar distance is A over square root of 2, 0, 0 plane 2 square plus 0 square plus 0 square, that is equal to A over 2, A by 2, 2, 0, 0 plane. Similar to this 2, 0, 0 plane. Another one is D 2, 2, 0, D 2, 2, 0 plane. The interplanar distance is A over square root of 2 square plus 2 square plus 0 square. 2 square is 4. 4 plus 4, 8. Root 8 can be written as root 4 into root 2. Root 4 into root 2. Root 4 is 2. So, this becomes 2 root 2. 2 root 2. That is the interplanar distance of D 2, 0, 0. Next come to D 1, 1, 1, D 1, 1, 1 plane. D 1, 1, 1 plane, interplanar distance is A over h square plus k square plus l square, that is equal to square root of 1 square plus 1 square plus 1 square A over root 3. A over root 3. So, therefore, in case of simple cubic lattice, interplanar distance are A by root 2 and A by root 3. For this body centered cubic lattice, interplanar distance are 2, 0, 0, that is A by 2, D 1, 1, 0, A over root 2, and D 2, 2, 2, A over 2 root 3. Similarly, for this face centered cubic lattice, D 2, 0, 0 plane A by 2, D 2, 2, 0, A by 2 root 2, and lastly we have D 1, 1 plane A by root 3. So, these are the interplanar distance in 3 different directions. See a simple cubic, body centered cubic, and face centered cubic. Example of this type. Now, if we consider the examples of these type of lattice, for simple cubic lattice crystals are very rare. Polonium is an example. Polonium is existed in simple cubic lattice. These type of lattice are very rare. Polonium is the example of this simple cubic lattice. For body centered cubic lattice, very important example is cesium chloride. Cesium chloride is existed in body centered cubic lattice. whereas polonium is present in the form of simple cubic lattice. These type of cubic lattice are majority, a number of crystals are existed in this face centered cubic lattice. Very important examples are sodium chloride, potassium chloride, copper metal, all these are existed in this face centered cubic lattice. Now, after knowing this interplanar distance, what is the applications of the measurement of this interplanar distance? Now, if you take the ratio of the interplanar distance in different directions, that ratio is the characteristic ratio of a cubic lattice. For example, if you take the ratio of the simple cubic lattice, the ratio becomes A by A is to A by root 2 is to A by root 3. So, this is the ratio. So, this ratio A by root 2, A is to A by root 2 is to A by root 3. Now, if you measure the interplanar distance and if you take the ratio, if that ratio is equal to this, or you can also simplify this ratio, 1 is to 1 by root 2 is to 1 by root 3. So, this is the ratio of the interplanar distance in a cubic crystal, and if you measure the distance, it is possible to measure the distance using a number of apparatus, spectrometers, it is possible. Now, if you measure the interplanar distance and if you take the ratio, if that ratio is equal to 1 is to 1 by root 2 is to 1 by root 3, the solid is existed in the simple cubic lattice. Similarly, if you take this body centered cubic lattice, the interplanar distances are for different planes A by 2, A by root 2 and A by 2 root 3. Now, if you take the interplanar distance ratio A by 2 is to A by root 2 is to A by 2 root 3. The simple ratio of this is 1 by 2 is to 1 by root 2 is to 1 by 2 root 3, 1 by 2 root 3. Now, if you multiply the whole thing by 2, you will get 1 is to into 2 means it becomes root 2 is to 1 by root 3, simple ratio, this ratio. So, if the interplanar distance ratio in different directions satisfy these ratios, 1 by 2 is to 1 by root 2 is to 1 by 2 root 3, or 1 is to root 2 is to 1 by root 3. If the interplanar distance ratio satisfies this ratio, if that is equal to this ratio, definitely we can say that the solid is existed in this body centered cubic lattice. Similarly, for this face centered cubic lattice, the interplanar distances are A by 2, 200 plane, A by 2 root 2, D220 plane, A by root 3, D111 plane. Now, you take the ratio of this, ratio of all the ratios are A by 2 is to A by 2 root 2 is to A by root 3. So, this is the ratio of this face centered cubic lattice. A by 2 is to A by 2 root 2 is to A by root 3. If we simplify that, this becomes half is to 1 by 2 root 2, 1 by 2 root 2 is to 1 by root 3. You see the difference. A by 2, that half is to 1 by 2 root 2 is to 1 by 2 root 3, but in this case it is 1 over 2 is to 1 over 2 root 2 is to 1 over root 3, and if this is the ratio of the interplanar distance in different directions, and that ratio is nothing but the interplanar distance ratio of face centered cubic lattice. So, now by taking the interplanar distance ratio, we can find out the structure of the cubic crystal, to which class it belongs. We can easily find out this interplanar distance ratio. Now, the problem is how to find out the interplanar distance ratio. To find out the interplanar distance ratio, an expression was derived by Bragg, and that equation is called Bragg's equation. Bragg derived an expression to find out the interplanar distance DHKL. To find out that, he proposed an equation, he derived an equation that is called Bragg's equation. We shall derive Bragg's equation now. Okay, we shall derive Bragg's equation. Now, Bragg's equation. So, let us derive this Bragg's equation. In this derivation of Bragg's equation, a monochromatic X-ray has been considered. Now, consider 3 different planes in a crystal, X, Y, Z. One is X plane, another one is Y plane, and another one is Z plane. Consider 3 planes in a crystal, and number of atoms or molecules are parallel to this plane. This plane is parallel to this plane, which is parallel to this plane. Now, you irradiate this with monochromatic X-ray. That X-ray, what happens? It will, this is X-ray, incident ray, and it will be reflected back on the first plane. Next ray enters into the second plane and reflected back. Now, you see. Now, what happens here? Let it be ABC, the ray ABC. AB is the incident ray, it is reflected back. BC is the reflected ray, and EFG is another ray which passes into the crystal and it is reflected at the second plane. Now, if you see this second ray EFG travels more distance when compared to the ray ABC. Now what happens? This distance is D, interplanar distance. So, we have to find out the D. To find out the D, this angle is the incident angle, that is called a glancing angle. This theta, this is represented by theta, this angle equal to this angle. Angle of incidence is equal to angle of refraction, that is also theta, and this is theta. The angle, this angle equal to this angle, incident angle, angle of incidence. Now, you see this is the distance, interplanar distance D. Now, you draw perpendicular planes here, perpendicular planes. Now, if you draw the perpendicular plane, this theta is equal to this one, this is theta. Similarly, this is also theta. Now, you see this line is perpendicular to this, so this angle is 90 degree. This is 90 degree, this angle is 90, and this angle is also 90 degree. Right angle triangle, right angle triangle. Now, you can apply the sine of this angle, that is sine theta is equal to opposite side by hypotenuse. Opposite side by hypotenuse. Opposite side of this theta, opposite side. Now, represent this as K and L, KL. Now, KF is the opposite side, KF is the opposite side, and hypotenuse is BF. Hypotenuse is BF. Hypotenuse is BF. BF is nothing but the interplanar distance D. Therefore, in place of BF, we can write D. So, D Kf by D is equal to sin theta, or Kf is equal to D sin theta. Kf is equal to D sin theta, where theta is the angle of incidence and D is the interplanar distance. Similarly, you apply the sine rule to this triangle. So, here also sin theta is equal to, this is theta, opposite side is LF divided by hypotenuse is D, is also D here, LF by hypotenuse is again D, therefore LF is equal to again D sin theta. Now, when compared to the ray ABC, EFG ray travels more distance. Therefore, this extra distance is travelled is equal to Kf plus LF. Kf plus LF is the extra distance. Kf plus LF is the extra distance, and a number of waves are excess when compared to the first ray, and that is represented by n lambda. The total extra length, extra waves that is travelled is represented by n lambda. Kf plus Lf is nothing but d sin theta plus d sin theta. D sin theta plus d sin theta is equal to 2d sin theta. N lambda is equal to 2d sin theta. N lambda is equal to 2d sin theta, where n is called the number of waves that are passed extra to this n, and lambda is the wavelength of the incident X-ray, and d is the interplanar distance, and theta is the glancing angle. And always when total number of incident rays and reflected rays are more, a bright spectra, a bright peak will be given, that is called first order refraction. Second order, number of orders of refraction peaks are obtained, and always this first order has got very bright, because more number of X-rays are passed and reflected back. Therefore, this n, which gives you the order of refraction, and when it is brighter, it is called first order refraction. This n lambda is equal to 2d sin theta. N lambda is equal to 2d sin theta is called Bragg's equation. So, n lambda is equal to 2d sin theta is the Bragg's equation. So, if we know the glancing angle theta and the bright line, that is order of refraction, and wavelength of the incident X-ray, if the wavelength of the incident X-ray and order of refraction and glancing angle theta, if these three things are known, D can be easily calculated. So, that is why to calculate D, we use Bragg's equation. N lambda is equal to 2d sin theta. A well-known equation in crystallography is Bragg's equation. N lambda is equal to 2d sin theta. Now, if we know theta, D can be calculated, and you calculate D in three different directions, and you take the ratio. You calculate D in three different directions, and you take the ratio of these interplanar difference in three different directions by changing the incident angle. You change the incident angle, and when there is a bright spectrum is obtained, and that is called the first order refraction. First order refraction or reflection, you take the interplanar distance of first order reflection in three different directions by changing the angle theta, and if the ratio is equal to this 1 is to 1 by root 2 is to 1 by root 3. The structure is simple cubic. Therefore, using this Bragg's equation, we can find out the interplanar distance ratio and also the geometry of the cubic lattice. Similarly, you measure the interplanar distance ratio using this Bragg's equation for a body-centered cubic lattice, and you take the interplanar distance ratio. If the interplanar distance ratio is this one 1 by 2 is to 1 by root 2 is to 1 by 2 root 3, that crystal belongs to body-centered cubic lattice. Similarly, you measure the interplanar distance at different angles in different directions for a face-centered cubic lattice and take the ratio. If the ratio satisfies this ratio equal to this ratio, 1 by 2 is to 1 by 2 root 2 is to 1 by 2 root 3, the crystal is in the form of face-centered cubic lattice. Therefore, the nature of the cubic lattice can be easily find out by taking the interplanar distance ratio, and the equation is A by DHKL is A by root K square plus H square plus L square is only for cubic lattice. Similarly, for other lattice, for trigonal, tetragonal, for all other lattice, the ratios are different, and those equations can be derived for different types of crystals. For this cubic crystal, this DHKL is equal to A by square root of H square plus K square plus L square. So, this is the expression for interplanar distance ratio where the intercept is A, and we can find out the structure, the type of the simple cubic lattice. So, in this way we can find out. Now, let us go to problems now. On the basis of this Bragg's equation and interplanar distance ratio, we can solve some problems. First problem is X-rays of wavelength 0.134 nanometers give first order diffraction from the surface of a crystal when the value of theta is 10.5 degree. Calculate the distance between the planes. Actually, wavelength is given, lambda is given 0.134, lambda is given, and theta is given, theta is equal to 10.5 degree, and also n is given, n is equal to 1, first order diffraction. So, therefore, we can use n lambda is equal to 2d sin theta, n lambda is equal to 2d sin theta. What we have to find out here? We have to find out d. D is equal to what? So, d we have to calculate. So, d is equal to n lambda by 2 sin theta, that is equal to n is 1 into lambda is equal to 0.134 divided by 2 into sin of 10.5 degree. Now, if you solve this, you will get the answer. The interplanar distance ratio d is equal to 0.368. That is how we can solve the problem. Another problem is to determine wavelength. So, theta we have determined, d we have determined, lambda and theta, how to determine. Now, second problem is what is the wavelength of X-rays which give a diffraction angle. Theta is equal to 8.4 degree for a first order diffraction for a crystal with interplanar distance 0.2. So, d is given, n is given, that is n is equal to 1 and theta is given. Okay. So, n is equal to 1, theta is equal to 8.4 degree and d is given, d is equal to 0.2 nanometer. So, we have to find out the wavelength. So, n lambda is equal to 2d sin theta, n lambda is equal to 2d sin theta, Bragg's equation, n lambda is equal to 2d sin theta, n is equal to 1 here, therefore, lambda is equal to 2, d is given, d is equal to 0.2 into sin theta is sin 8.4. Now, if you multiply this, you will get wavelength lambda is equal to 0.0584 nanometers. So, that is how lambda can be determined. Similarly, theta can also be calculated. Here in the third problem, X-rays of wavelength 154 picometer are diffracted by 200 plane of a cubic crystal. At what angle would be the maximum reflection occurs? Now, given lambda is equal to 154 picometer and by 220 plane, 220 plane is given D220, that is equal to diffracted D220, that is a plane given, and what angle theta is you have to calculate, theta you have to calculate. So, this D220 lambda, n lambda is equal to 2D sin theta. So, here we can use n lambda is equal to 2D sin theta. So, here n is for 200 plane of a cubic crystal, at what angle would be the maximum reflection occurs. Now, here we have to find out theta here. D can be calculated, interplanar distance D A by root of h square plus k square plus l square. Using that formula you find out D, lambda is given, and n is, because maximum reflection indicates that n is equal to 1, n is equal to 1. N is equal to 1 is given, D 220 plane, you find out the distance of 220 plane, that distance is A by square root of h square plus k square plus l square. You find out the distance and lambda is given, you substitute this, you will get the answer theta is equal to 16 degree. So, that is how by knowing the other factors one unknown thing can be determined. That is about the calculation. So, in today's video class we have discussed the ratio of the interplanar distance. By knowing the interplanar distance ratio, we can find out the nature of the cubic crystal, and also we have derived Bragg's equation. Using this Bragg's equation and interplanar distance ratio, we can find out easily.
Because oxygen, due to small atomic size, it is always,
we can find out the structure of the cubic lattice, and also in these three solved problems we have determined interplanar distance D, and we have determined the wavelength of the X-ray used, and also we can determine. So, by knowing other factors unknown can be calculated. So, that is the summary of today's class. We shall meet in the next video to continue with this topic. Thank you.